So before the fire alarm took off, it's talking about catalysis. So the kind of the point of last class lecture and this lecture, among other things, is like what affects chemical reactions, and there were a couple questions on how we control them, and we talked about concentration and temperature. So concentration is important, and is because if there's more stuff, there's more collisions, there's more likely to be a chemical reaction. Temperature is important for a few ways. One of them, if things move faster, that means there'll be more collisions. The other thing is that there is the activation energy. So there needs to be enough energy to overcome the repulsive barrier between two molecules. And then the last thing is catalysis. What do catalysts do? They provide an alternate pathway. So some things about catalysis is they are not consumed in a reaction. So if you have a catalyst, the catalyst is not consumed. So the catalyst sticks around. And for instance, if you have this reaction here, ozone plus oxygen radical reacting to form two oxygen molecules. And this is a very important reaction because up in the ozone layer, this reaction takes place in the presence of radiation, UVB radiation specifically. And this reaction helps to block much of the UVB radiation coming from the sun coming down to the earth, and to the surface of the earth, I should say. Also, it works both ways. So UV causes it to go this way as well, oxygen reacting to form ozone and oxygen radicals. So this reaction is one of the many that goes both ways, and as it goes both ways, it absorbs a lot of UVB radiation and it protects the earth. So, and that happens in the stratosphere. Are you guys familiar with the layers of the earth? So we're in the troposphere. So this is the troposphere. So the surface of the earth, the troposphere, then there's a stratosphere, then above that's called the mesosphere, then above that the thermosphere, then exosphere, or outer space. So, and the atmosphere is about 60 miles high. So, and it depends, the atmosphere is not uniform across the earth. And so and it changes, about 10 miles or so is the troposphere. It can, well, it's maybe not 10 miles, I think. Actually, I'm not sure. So maybe 7-ish. So, but it varies. Although, and the ozone layer is in the stratosphere. So ozone here in the troposphere, that's bad. Ozone in the stratosphere, that's good. So, and ozone here in the troposphere, it also blocks UV radiation. So if you ever notice when it's a very polluted city, you don't get, at least for me, I'm as fair as they come. Well, I guess I'm not an albino, but I get sunburn easily. And I notice that, like, if I'm in like LA or something, I don't need as much sunscreen because of all the pollution in the air. Okay, so not consume the reaction. What do I mean? So here is, so chlorine radical can catalyze the depletion of ozone. So chlorine radical can, and this is all gas, chlorine radical can react with ozone to form chlorine monoxide plus oxygen. Chlorine monoxide can react with oxygen radical to form oxygen, and then the chlorine radical pops back off. So you can see that and if you look at the overall reaction, this cancels and this cancels, and you have O3 plus O makes O2, two O2s, and that's exactly right there. So the overall reaction is the same, and the catalyst is used, well, it participates in the chemical reaction, but it's also regenerated. So they can go on, it can destroy more ozone. So that's one thing about with catalysis. So this is an example of a bad reaction. So we don't want ozone depletion. But I mean, of course, we use catalysts for other things, and I'll talk about that later. It turns out this is wrong. Ozone depletion is not a homogeneous reaction. What really happens is that it's a heterogeneous one. such that if you have an ice crystal or so a piece of volcanic ash, that they all absorb on the surface of the solid. And this is actually bad news because it consumes it much more quickly. So heterogeneous catalysis is very, very powerful, much more powerful than homogeneous same phase. If you wonder how it works in the liquid phase, you typically have some sort of metal center, and it usually forms an octahedral complex. And you can have things, and this is not how it will work, but you would have things that absorb alongside, and then the chemistry happens on that complex, and that would be for like liquid phase. So this happens quite a bit for liquid catalysis. Of course, as I mentioned, this is not how ozone depletion works. But it would be something like that. So an example of heterogeneous catalysis, we talked a little bit about petroleum plants, and platinum. Platinum is a very, very active metal. It doesn't react very much, but it's very catalytically active, and such that many things dissociate on it. So ethene. So I mentioned ethene before. It's did I tell you? Or I guess I did talk about this. The autocatalytic nature of ethylene, ethylene, the same thing. It causes fruit to ripen, and that's also where we get polyethylene. But when hydrogen, so you can see hydrogen approaches the metal surface, and then it breaks apart. This is known as chemisorption because there's actual chemical reaction that happens on the surface. Ethene comes here on the surface, ethene, ethylene, and this is known as physisorption. So the molecule stays together, so it's still the same molecule, but it absorbs into the surface. And then on the surface, the chemical reaction progresses, and then the new molecule pops off. So this is done quite a bit in oil refineries. Depends on what molecules you want to make. So if you want to cycle, if you have a long chain molecule and you want to cyclize it, you can take long molecules, you can break them apart. That's known as cracking. They usually use a different catalyst for that. Some sort of zeolite is what they use. But platinum and palladium, they use a lot for reforming and also for things like this, where you take and you turn an unsaturated hydrocarbon into a saturated one. So unsaturated means double or triple bonds. You can go the other way as well. You can go from saturated to unsaturated using these catalysts, but usually you have to poison them because it's so fast going the forward direction. You poison it with stuff like sulfur. So, and these reactions are very, very fast, these heterogeneous catalysis, and they're very, very effective. Oh, I guess I can show you one. I have my molecules in action. Come on. And platinum is one. Where's platinum? Right here. So you see here, here's, what do they put, ammonia? Yeah, so there's ammonia. And if you ever smelled ammonia, knocks you off it's really, it's a strong smell, and it can really, whenever I smell it, like, whoo, it actually can make you pass out. So you can see that the heat up the platinum there, and do a little bit of vapors there, it'll start to make it glow more, it'll react. So, it's heterogeneous phase because that's solid platinum and then vapor ammonia. You can see it's glowing more and more. It doesn't mean like catalysis will happen at any temperature. You can see that Theodore Gray heated up with a Bunsen burner, or I think it was a torch. Well, heated up with a torch before he put it in there. But so it doesn't that you don't need activation energy. It's just the reaction takes place much lower temperature than it normally would. Okay, so, and where do we use this this type of catalysis, and one of them is in the catalytic converter of your car. So if your catalytic converter, what we've done, and this is one of the examples of accidental nanotechnology. So platinum and palladium, very expensive. They're very expensive metals. But they found out that if you take clay, a zeolite, and you hit it with, it has platinum or palladium in small amounts in it, it makes it a very viable catalyst for complete combustion of hydrocarbons, and also breaking apart nitrogen oxides. So in your car, in your engine of your car, oftentimes there's incomplete combustion, which means you have carbon monoxide, and there's also leftover hydrocarbons. So why do we care? Carbon monoxide is poisonous. So there is an actual human health hazard. That's what the Environmental Protection Agency calls it. It's a human health hazard associated with this compound. Hydrocarbons are dangerous because you can form photochemical smog with them. So photochemical smog is the brown air you see in Los Angeles. Like have you been to LS? I have. Like, you know, you can kind of see sometimes off in the distance there's this kind of brown haze. That, among other things, it comes from unreacted hydrocarbons. Some photochemical smog is natural. Trees give off hydrocarbons, so you can get photochemical smog from trees, but humans give off more, so generally speaking. And then the last one is nitrogen oxides. And nitrogen oxides, they cause, well, there's a human health hazard for them too. Causes lung damage, and like they're very pungent smelling molecules. I mean, of course, there's good and bad. Nitrogen oxides are important, and they come about naturally through things like lightning strikes. And that's part of the nitrogen cycle for the earth. So nitrogen is a primary plant nutrient. So it's important for plants to get nitrates because that's how they grow. So one of them is naturally found from lightning storms, from electrical storms. Of course, if humans start pumping a bunch of nitrogen oxides in the atmosphere, we get more acid rain. So nitrogen oxides react with oxygen and water to form nitric acid and nitrous acid. And those are acids, and they drop the pH of the rainwater. And depending on where you're at, it's not a big deal. Here in Hawaii, it wouldn't be a big deal because we have terrible acid rain. And sometimes the pH of the rain is as low as 3 because of the volcano. So the plants here have really adapted to the acidity of the rain here in Hawaii. But if you're somewhere like in Colorado and you get a bunch of pollution from like California or something like that, and then the rain becomes acidic, it can really ruin the root systems of many trees. And so that's one of the environmental impacts of nitrogen oxides. So that's just from us humans dumping more and more into the atmosphere than that should. So it was accidental because it was accidental nanotechnology because we didn't realize what we were doing. But this is an image of what it would look like. You have the platinum surface or palladium surface, and you had these cluster. I'm sorry, this is not platinum. This is the platinum. This is the zeolite, and it's kind of like honeycomb. It's like a honeycomb-like structure, and then you have these islands of catalyst, and then the reactions take place there on the surface of those islands of the catalysts, and that way it's a lot cheaper than using like strips of platinum. You can have a little bit of platinum and a lot of oxides. And then it makes it feasible to put this on cars. I mean, because if we all had to have strips of platinum on our cars, I mean, then cars would cost a lot more than we could afford. So, and here's what I mean by human health hazard. You can see that the Clean Air Act, after it was passed in 1980, I think it was before that. I think it was in the 70s. But anyways, you can see that there's been a huge change in pollution levels because of catalytic converters. And carbon monoxide, well, especially carbon monoxide, this is the source of carbon monoxide is almost exclusively from transportation. I mean, you can get it from fires, but really, at least the anthropogenic, so human-caused pollution, it's almost entirely from transportation. So I mean, it's not gonna like. There's more than transportation, just cars. There's jets as well, right? And boats. Boats oftentimes use fuel oil or more frequently bunker fuel, which is an unrefined petroleum product. And there's even other things like lawnmowers. You know, like lawnmowers generate carbon monoxide, and we don't put catalytic converters on lawnmowers. On my lawnmower, I have an electric one. Well, it's kind of bulky, but it's more than I'm cheap because I got it for $80 on Amazon, and you have to buy a gasoline powered one and costs like $400. I was like, meh, I got a small yard. I'm fine with the electrical one. But there's talk of putting catalytic converters in some states on lawnmowers. Another accidental form of nanotechnology was rose windows in some of the cathedrals. If you've ever been to Europe, they have a lot of times in the towns, they have the huge cathedrals and the very pretty stained glass windows. And they had a hard time figuring out where they got a pink and purple color. And they found out it's gold. And specifically it's gold nanoparticles. And in the medieval times, they found out if they heated gold and treated it a certain way, they would get pink or purple glass depending on how they played with it. And it was accidental, and it was just by trial and error. But it turns out that we were doing nanotechnology. So interesting how that. I mean, we do nanotechnology purposefully now, like with our computers. So the transistors in our computers are in the order of hundreds of nanometers. So we can do nanotechnology now. But it's interesting that we had accidental nanotechnology. Unfortunately, I think this is the rose window was for Notre Dame. Unfortunately, that's burnt down. So there's a hope that we're rebuilding it. I don't play video games anymore, but I think does anyone play? I think it's Assassin's Creed. There's actually they're actually very grateful because I think it was Assassin's Creed, but they mapped out the inside of Notre Dame in France, and they're gonna the video games archives are gonna help them rebuild it. So, but it's very beautiful. I'm fortunate that I got to see it with my own eyes before it burnt down. So if you ever, oh well, Paris is an interesting place to visit if you ever get the chance. But I guess you won't be able to see the good old Notre Dame yet. Hopefully they'll rebuild it soon, and at least now we know we didn't lose well, we gained the knowledge. We know how to make the pink glass now, so that's good. So last thing, enzymes are biological catalysts, and enzymes are very, very important to biological life forms because so many of our chemical reactions, they have to happen fast and they have to happen very site specific. And that's what catalysts do, is they have very efficient and very site specific chemical reactions, and they're very efficient too. And so many things, some of the more simple ones, like if you see here, so this is breaking apart of glucose. So I'm sorry, sucrose. Sucrose is a disaccharide, meaning two sugars, and it breaks into glucose and fructose. Our body mostly runs off of glucose. We can also run off of fructose, but glucose is kind of our primary preferred fuel. But we also like fructose as well. I guess in some ways our body runs better off of fructose because because if you take glucose, it just goes right in your system. Our body kind of regulates sucrose a little bit better. Regulates fructose a little bit better. We also like the flavor of it more. So if you've heard of high fructose corn syrup, so fructose, we humans prefer the taste of fructose over glucose. But if you ever need a boost of sugar, there's nothing like glucose. Actually, in my backpack, my teacher bag of tricks, I actually have a source of glucose right here. Bottle caps. Some candy, it's straight glucose. This is straight glucose. But that's more for me. If my brain ever stops working, you'll see me start popping candy, because actually glucose goes in your system like that, just pops right into your system, and your brain runs off of sugar. So anyways, yeah, so the way that an enzyme works, the idea is that you have the fast step, the enzyme plus the substrate forms an enzyme substrate, and then the enzyme substrate then breaks apart into the enzyme plus the product. And notice that the enzyme is not consumed in the process as a true catalyst. It pops back off and then can be used again. And so breaking sugar apart into fructose and glucose, and I'm saying sugar because sucrose is table sugar, what we normally call sugar, and it breaks apart the sucrose. Of course, there's many other enzyme reactions, and what we found out for enzymes is shape is extremely important. If you change an enzyme's shape, you change its function. So it also explains a couple things. It's the reason why we cook our food. So we cook our food, and why do we cook our food? Well, it makes it safer. Why does cooking our food make it safer? It denaturizes all the enzymes. So the word denaturize, that means that it's denatured, it changes its shape, it doesn't function anymore. And there's a few ways you can denature proteins. Easiest and most common one, temperature. The other one is pH. So if you take altering the pH high or low, you can change the shape of, well, you will. The enzymes change shape. Depends on the enzyme to how much it'll be deformed. So certain foods can be cooked, quotation marks, cooked, using acids. So things like ceviche or lomi salmon. So lomi means rubbing, right? So, and you use acidic foods, so tomatoes, limes, to cook things like fish using without temperature, without heat. So you can denature proteins and therefore make it safe. So that's how we make our food safe. And like I said, if the shape changes, it doesn't work. Oh, another thing that can change the shape is heavy metals. Certain heavy metals can just sit inside proteins, and it alters their forms, and it either makes it work not as well or doesn't function at all. And certain, especially neurotoxins, lead and mercury can change the shape of many enzymes, and that's where the toxicity of certain heavy metals like lead and mercury can come from. That doesn't mean all toxicity from all metals comes from that. So cadmium, for instance, is a toxic metal. Cadmium replaces calcium in your bones, and that's the primary toxicity of that. So so that doesn't mean every single metal works the same way for its toxicity, but one of the ways that it can work is by changing the shape of enzymes. And so for us humans, what I mean by the shape is important. Like if you get a 3rd-degree burn, like so if I went and got a 3rd-degree burn all over my fingers, would I be able to bend them? And the answer is no, because there's a lot of enzymes that take place in simple things like motion. So that's one thing with temperature and the danger of that. So there you go. I'm done with this chapter. And I know that we were rudely interrupted by the fire alarm last time. Although it was weird, I got to see some of your faces for the first time. I think, Dan, that was the first time I've seen your face, and same with you, Dennis. And here we are wearing masks. It's like, whoa, that's what your face looks like. What? usually you just have your Dan Vu. I usually just see your name, or is that, I know Kiana's here, I just see her name, or maybe I don't know, maybe they change it for me because anyways, doesn't matter. Does anybody have any questions about anything? So I know a lot about kinetics. I mean, of course, chemistry is a very broad subject, but I studied kinetics in grad school, so I do know a lot about this. So if you have any questions or advanced questions, you can always hit me up after. Questions are fun anyways. All right, so I guess this is where it should have gone. Been started today. I don't know how far we'll go through, but it's fine. We got plenty of time. So this is the next chapter. It deals with equilibrium. Now, the good news is that you're done with the hardest chapter. So chapter 15 is the hardest chapter because it's calculus based. So now we're on to chapter 16, and here on out, it's only algebra. So no calculus or calculus concepts. And I mean, even though chapter 15 kinetics, it's calculus concepts, but taught with an algebra twist. So equilibrium, we're no longer worried about how fast we get there, which is the previous chapter. With equilibrium, we are now, we're only looking at what happens as it reaches equilibrium, or as it's reaching equilibrium. So in the word equilibrium, like one of the things we often talk about is balance. So when things are at equilibrium, you're at a sense of balance. And even you can, for certain symptoms of like head trauma is what they say, loss of equilibrium. And like, I mean, here I am, I'm standing up straight and it's like, I feel pretty relaxed right now, but I actually am doing quite a bit of work. And my feet, if you've ever hurt a toe or sprain an ankle, it's hard to stand afterwards because like it's amazing how often you use those little muscles and stuff, in your feet and toes to stand up. Also my back. So I have my paraspinous in my back is engaged to make sure that my spine stays erect. So even some of those muscles are called the erector spinae that keeps your spine erect. So there's much going on, and all that I'm thinking about, I can feel my quadriceps flexing, as I'm kind of swaying a little, right? So that's equilibrium. It looks like I'm doing nothing, but actually there's quite a bit going on. So just like things in chemical processes. And the idea with equilibrium is for chemical reactions, that means they can go both ways. So frequently in last chapter, we say, this goes one way. And the answer is usually chemical reactions go both ways. Some of them infrequently go one way, or many times there's one way favored. So things like combustion. So if I'm burning, like I have my textbook here. If I'm burning paper, and paper is quite a bit of glucose, the forward reaction of glucose going to carbon dioxide and water, that's way favored over carbon dioxide and water forming glucose. Can it happen? Yes, it does, and maybe in small amounts, but that's predominantly in one direction. So there are many reactions, though, and many simple ones, that it's really important that the reaction goes both ways. And one of them, for instance, is hemoglobin, and I'm fixing it to HB. Hemoglobin plus oxygen makes hemoglobin oxygen complex. So it's actually more complicated than that. Hemoglobin, the protein, so hemoglobin is a protein that our red blood cells have that we use to transport oxygen in our blood. And hemoglobin actually has 4 heme groups, and they're like blobs. So it's kind of like hemoglobin's kind of like you have 4 heme groups, and they have an iron center in it, and you have the iron as a bunch of protein around the iron, a lot of amino acids. And the idea with hemoglobin is when you have oxygen, and oxygen comes and then attaches the hemoglobin, And actually the molecule forms such that it's easier for other oxygen to then join after it. So that's another feature of hemoglobin. It's interesting. It's easier to uptake oxygen the more oxygenated you are. So it's really 4 oxygens on hemoglobin, or at least it should be 4. And it's really important, though, that this reaction goes both ways, right? Because you want your oxygen depleted heme groups to absorb oxygen in your lungs, and then you want it to the hemoglobin to release oxygen when it comes to your cells. So you don't want this reaction to go one direction such that hemoglobin attaches to oxygen and then nothing happens, right? You want this to go both ways. Another reaction that you want to go both ways is carbon dioxide plus water forming carbonic acid. So this is how our body transports carbon dioxide from our cells to our lungs. So oxidation of glucose, our primary fuel, right, forms carbon dioxide and water. Water we can deal with, right? We actually need quite a bit of water, at least us humans. Some animals don't need to consume water. They can just get enough water from they need from combustion. But we need extra water as humans. But what we don't need, those humans, is a large amount of carbon dioxide. And so what happens is the carbon dioxide absorbs into the water in our bloodstream. And then when we get to our lungs, what do? We exhale, and then the reaction goes the other way, and then the carbon dioxide leaves our body. Although carbon dioxide is also important, it's not just a waste product, we use it. And it's amazing how these biological systems work, how redundant they are, and how like even a waste product like carbon dioxide is in some ways a nutrient. We use carbon dioxide to regulate our blood's pH. So it's part of our buffer system. We'll talk about buffers in a few chapters. But if you've ever hyperventilated before, what do you do to someone who's hyperventilating, besides, pat the person on the back? You give the person, they say paper bag, but a bag, something to breathe into. And the reason for that actually is to absorb carbon dioxide. Because otherwise, if you hyperventilate too much, you can get a condition called alkalosis, which means your blood pH goes up. And the carbon dioxide forms carbonic acid, and this is carbonic acid. That acids make pH drop. So that's one way you can make your pH drop, is to hold your breath. If you do that, your pH, my blood's pH is slowly decreasing. It's a lot harder. I like to breathe though, so I can't hold my breath for too long. But yeah, so it's amazing that even carbon dioxide, you think it's a waste product, but we use it. But of course we generate too much, so we do have to expel it. And these are biological reactions. So here's a chemical reaction that's non-biological that goes both ways. Hydrogen plus iodine make 2 hydrogen iodides. I'll show you a picture of that later. But also what I mentioned is that relative sizes of equilibriums matter. So there's another biological feature. So for us mammals, we carry our offspring inside of us, inside of our own bodies, versus reptiles. Well, I guess echidnas and platypuses or platypi, they still lay eggs, but the rest of us mammals, we carry our offspring internally. And our offspring, of course, when they're inside of us, well, not me, I'm male, but a pregnant female will have offspring inside of them, and the mother needs to have oxygen, but so does the child. And so the offspring will then, inside of that, the offspring has a type of hemoglobin that's slightly more binding than adult human hemoglobin. And then so the fetal hemoglobin will then draw oxygen away from the other hemoglobin. And that's an interesting feature. So Of course, this has got to be a balance because it can't be so strong because the offspring needs to have oxygen in order to grow and function. And so there has to be, the reaction has to go both ways, but it's slightly more binding than than adult hemoglobin. So interesting thing. Of course, after the child is born, that type of hemoglobin is no longer produced. So I also have in my note, forward rate equals reverse rate. That's the idea with equilibrium, is that the rate both ways is constant. It's steady state, if you will. So, and if you mentioned before this reaction, come on, iPad. Okay. We have hydrogen plus iodine making 2 hydrogen iodides. And if you look at this graph, the y-axis is concentration, x-axis is time. And in the beginning, if we start off with all reactants and no products, and then let the reaction go, the reaction will progress forward until it gets to a point where the concentration doesn't change. So you can see here, hydrogen iodide is increasing, and then it stops. At least it doesn't stop. The change overall, the overall change is constant. So meaning in the equilibrium, we have a dynamic equilibrium, meaning that it looks like nothing's happening, but the chemical reaction is still happening. I mentioned dynamic equilibrium before when it came to phase changes. So when water is boiling, so when you're boiling water, inside the bubbles, as the water is boiling, water is both leaving, going to the vapor phase, and it's also condensing. So it's happening both ways. And same thing with a chemical reaction. So in this case, hydrogen iodide is reacting to form hydrogen and iodine. But at the same time, hydrogen and iodine are reacting to form hydrogen iodide. So the reaction is actually happening in both directions, but at the rate of the forward is the same as the rate of the reverse, and it doesn't change. And that's equilibrium. So, and it's where the outside viewer looks like nothing happened, like me right now. I'll stand in front of the podium. Sorry, Kiana. I am at equilibrium. I am balanced. Is that really what's going on? No, like I said, my toes, I can feel, now that I think about it, I can feel my feet and my whatever, it's the more ligaments, but there's muscles around my legs. They're keeping me standing up straight. So I'm doing something. I'm not just doing nothing. It looks like I'm doing nothing other than talking, but balance-wise, it's very important that I'm doing something. This is equilibrium. Same thing with a chemical reaction. It's going forward and reverse. An analogy is immigration. So let's say that there was no political divide. I mean, I know there's more people in South Korea than North Korea, for instance. But let's say we have 2 equally awesome or 2 equally, not so awesome places. So, and if there is, say that there's a barrier between them, and suddenly you drop the barrier. So let's say you have the fence here, and then now you open the fence and let people go wherever they please. In the beginning, if you have lots of people, say for whatever reason, I'm trying to think a place that looks about the same. I almost want to say the Dakotas because they have the same name, North Dakota, South Dakota. What's in it? Maybe. What? Oh, Berlin. That's a good one. Yeah, that's a good example. Yeah, East and West Berlin. So where you suddenly have you have the more wealthy, more resource West Berlin and the more starved East Berlin. What's going to happen when the Berlin Wall comes down? A lot of people rushed over to West Berlin, but then over time, it's people are still moving back and forth, but it's kind of equilibrated. Well, it's equilibrated, whereas the rate in this direction is the same as the rate in that direction, and that's equilibrium. So it's not like immigration and immigration doesn't happen. The idea is that it evens out. So, of course, this deals with people and immigration and emigration. So let's say we have something with a large number of molecules. I don't know, one of my favorite numbers, like 6.02 times 10 to the 23rd, for instance. That's a big number, right? More than the whatever 5 million-ish people that are in Berlin. So then because of those huge numbers that we deal with in chemistry, I mean, it's more or less the same. Everything is pretty even, driven by probability. Okay, so let's have the most generic chemical reaction you've ever seen. Little a stoichiometric ratio of reactant A plus little b stoichiometric ratio of species capital B. And these arrows, so if it's an arrow like this, it's an ugly arrow. That means, I guess you can't see it in the gray. Maybe I'll just change the blue. There you go, easy to see. So that one direction arrow means the reaction goes one way. And equilibrium, we kind of give it this swipe up that way. And you can do it arrow-wise, but it's just because I can do this with one stroke of the Apple Pencil. So, and I wonder about some of these things, like these writing things that we have, how they're going to be, maybe they'll be obsolete in a few years when we don't write anymore. Who knows? But that's they have just single arrows like that because it's just 2 pen strokes. But anyways, this means equilibrium. It means it's going in both directions. And as for products, we have lowercase c stoichiometric ratio of product capital C and lowercase stoichiometric ratio of product capital D, little d of capital D. And the equilibrium constant, so we have an equilibrium constant, and an equilibrium constant is temperature dependent, much like the rate constant. Rate law constant is little k, equilibrium constant is capital K. My problem is my lowercase k's and capital K's look pretty much the same. Sorry about that. But equilibrium constant, this constant does not change at a given temperature. And the equilibrium constant is the products over the reactants. And remember that these brackets means concentration in moles per liter. So products over the reactants. So we have product capital C raised to the stoichiometric ratio little c, and that the concentration of this product C is its concentration at equilibrium. So if these concentrations of the products and reactants are not at equilibrium, you get a different value. But at equilibrium, that this ratio of the reactants and products, well, I guess in this case, products over reactants, raise their stoichiometric ratios in the balanced chemical equation are not going to change. So that's the other thing with balanced chemical reactions. I mean, if you remember from last semester, make sure it's balanced, because if you don't have a balanced chemical reaction, then you're going to get the wrong value for equilibrium constant. So that's another thing where you have those skills need to carry on. So in equilibrium constant, I think this is relatively easy. Express the equilibrium constant for this reaction. So methanol vapor in equilibrium with carbon monoxide and hydrogen. So to apply this, it's just the equilibrium constant is the products, carbon monoxide concentration, hydrogen all over methanol concentration. And I'm missing something. You have the 2 here, so you need a 2 there. So 1 is implied, they're all so methanol and carbon monoxide stoichiometric ratio are 1. You do not need an exponent because, no exponent implies an exponent, like an exponent of 1. You need to have the 2 exponent for hydrogen. So that means that this 2 needs to appear there. So, question with this one? How are we doing so far? Any questions about equilibrium in general? So let's talk about the significance of the equilibrium constant and more of its magnitude. So, and I always think of it as products over reactants. So if the equilibrium constant is significantly smaller than 1, so if the equilibrium constant is very, very small, so that means it's a small number. How do we have a small number? So that means that the products is a small number and the reactants are a big number, right? To have a fraction that's a small fraction means that you have a tiny numerator and a large denominator. So that means in the equilibrium constant is product over reactant. So small numerator, small products, large denominator, large reactants. So that means mostly reactants. That means that the chemical reaction does not proceed very far forward. And many, many reactions do not proceed very far forward. We're going to study acids and bases coming up next chapter. No, is it next chapter? Yeah, it is, next chapter. And most acids and bases, they have a very small equilibrium constant. So that means that acids and bases tend to like to stay molecular more than they do to break apart. So then we can have equilibrium constant is about 1. So it means neither reaction is favored, neither direction is favored. And the reaction proceeds about halfway. And there are many reactions like this too. The hemoglobin oxygen. This is an example of one that's close to, an example of chemical reaction that's close to 1. Because it happens both ways, right? So right now in my body, I guess I'm exhaling. So as I talk, inhale. Okay, as I inhaled, actually, I guess there's still air in my lungs, but the blood in my lungs right now are absorbing oxygen, and then the rest of my body, they're desorbing, and the oxygen is being brought off. So this reaction is happening both ways in a relative equal amounts, right? So that means the equilibrium constant for oxygen absorption is about 1. And then if K is significantly greater than 1, so to have K bigger than 1, that means that the products is a big number, so the numerator is a big number or a normal number, and the denominator is a very small number. So let's say we have a numerator of 1, and like a 1, and then a denominator of 0.00001. So I don't know, a millionth. I didn't count my zeros. So if we have 1 over a millionth, then that equals a million. That's a big number. So when you have a K, that's like 10 to the 6. So if you have something like 10 to the 6, that means that you're taking 1 divided by, there we go, right? You have a number, a normal size number over a really, really tiny number. What does that mean? It means you have more products. Products are favored, so the reaction tends to proceed forward. So that tells us about K. So, okay, so here's another, okay, it's K. For instance here, nitrogen and oxygen reacting to form nitrogen monoxide. And this is a small number. So it means it doesn't really proceed that far to the right at a given temperature. So we have nitrogen and oxygen in the atmosphere right now. Does that mean it's reacting to form a little bit of NO? Yes, it is. Is it significantly amount? No. No, it's not. Nitrogen monoxide, it's a very pungent gas. Not only that, it does have a curious function, at least for males. It causes erections. So we would probably, I guess we would know if there was a lot of nitrogen monoxide in the air here, besides the fact our lungs would be burning. So, and let's see here. Another example and some terms, I should say. The reactant side, we call the reactant side left, and we call the product side right. So if I say left is favored or right is favored or shift left, shift right. So shift left means towards reactants. Shift right means towards products, because I know, so I know this is my left hand, but stage right, right? So that's your right, my left. So stage right is the reactants. I'm sorry, stage right is the product side. Stage left is the reactant side. Still messing up my mind because calling this stage left. But okay, and another reaction that proceeds farther right. So hydrogen plus bromine making hydrogen bromides, 2 hydrogen bromides. It's a very high equilibrium constant. Sometimes you'll see an equilibrium, it'll be kind of written like this. That means that one side is favored. But typically though, you see the symbol. Typically you just see the symbol and you given a K value. And you the chemist needs to interpret the K value. So at a certain temperature, the reaction of 3 hydrogens plus nitrogen forming 2 ammonias is 0.95. What do you think about this reaction? Do you think it favors products, favors reactants, or goes about halfway? Yeah, it's close to 1. It goes about halfway. And oftentimes, though, to give you an idea with chemical reactions, if it's between, say, 0.001 to about 1,000, the K value, it just depends. It depends on the chemical reaction. If you see a K value of, in this range, of 1,000,000th to 1,000, that's not a million, I'm sorry, milli, 1,000th to 1,000, that means you're probably going to see all species. So I mean, you'll see both reactants and products. And so why do we care? Well, it depends on the context. So if you have a chemical reaction such that you're making something, and if a certain product is really favored in one way, then maybe you want to let the reaction go for a long time. Maybe you don't want the reaction to go for a long time, because sometimes the small thing that's being formed is something toxic. So that way you're like, okay, I want to cut this chemical reaction off as fast as I can because we're making this toxic material. So I'm just going to have a really small reactor and just recycle the things so very, very often. So it's these Ks do tell you important things. And if you have a K that's, like I said, in this range, then it just depends. Like maybe this is an uncomfortable situation where you don't want something. Maybe the small thing is a very, very valuable product. It really just depends. So, okay, so some relationships with the equilibrium constant. If you reverse the reaction, you invert the equilibrium constant, right? So let me simplify it such that we have the generic reaction. A reactant goes to free B products. The reaction, that's the chemical, the equilibrium constant, thank you for the words. The equilibrium constant is products over reactants. So the equilibrium constant is B over A. If you reverse the reaction such that the product is now the reactant, the new equilibrium constant is the inverse of the old equilibrium constant. Inverse just means you flip the fraction, right? So you flip the fraction, and the new equilibrium constant for the reverse reaction is A over B. The original one was B over A. The new one is A over B. And it's going to be the same thing with the more complicated chemical reactions. So also, if you multiply the chemical equation by some factor, you raise the equilibrium constant to that factor in terms of a power. So if you have A in equilibrium with B, K is B over A. So now I'm going to multiply by some factor N. So we have N of A reactants in equilibrium with N of B product. Our new equilibrium constant is going to be B over A, both raised to the N power, which is the original equilibrium constant raised to some power N. So that's what happens if you multiply an equation, you raise N to that power. And for multiple step reactions, say that we have A in equilibrium with some intermediate, and the intermediate is then into some equilibrium with the product C. And that means then if you have the overall chemical reaction, A in equilibrium with C, the overall, the intermediate goes away, and we just look at the overall reaction. That the equilibrium constant is product C over reactant A, raised to whatever stoichiometric ratio. So let's do this for one. Consider the chemical equation equilibrium constant for ammonia synthesis. We have nitrogen plus 3 hydrogens forming 2 ammonias, and the equilibrium constant is 3.7 times 10 to the 8th. What's the equilibrium constant for this following reaction? We have ammonia breaking apart into 1/2 nitrogen and 3/2 hydrogen. So what are we doing? We are inverting it, and we are multiplying it by 1/2. So this new equilibrium constant is, it's going to be K prime is going to be, you invert it, so it's 1 over K, and then you take the square root of it. So invert it and square root it. And so that means it's going to be 1 over 3.7 times 10 to the 8th raised to the 1/2 power. And what the heck is that? Something close to 2 times 10 to the, wait, 2 times 10 to the 4. So they'll be like 5,000. What example is this? Oh, the numbers changed in this edition. All right, I'll calculate it on my calculator. I didn't realize that. So anyways, 1 divided by 3.7 exponent 8. So this is going to be, oh, I have a free calculator, so apps, so I have to look at the ads. 1, 2, 3, 4. 5.1, 2. Actually, no, I guess it's 10 to the minus, geez, 5. Okay. So put in your calculator, you get this number. And so what? Why do we care? Excel spreadsheets. So if I'm keeping track of things, and I've seen this for chemical plants, and I mean, looking at the equilibrium expressions for things, and they want to see how much of a certain reactant, how much of a certain product they are. What do? You make a spreadsheet, and you put in the equations for how much you should generate in each of them. And if we're looking for the concentration of a certain species at equilibrium, we'll have just a cell, that has the equation, and then when you put in your information, out pops the answer. So it makes it much easier when you're designing a chemical plant, or if you want to figure out how much stuff you want to make for the day. Like, okay, I need to, so for you as you're planning the day or the week, like, I want to make this much ammonia, and this is my conditions. How much am I going to make? Or maybe this is a nasty product. Like, okay, how much of a disposal of this nasty product do I need to plan into my function of the plants? And so these ways of inserting these specific values into your output for your spreadsheets or programs are then very useful. So this is where we'd use that for that. Anyways, going back, we have synthesis of ammonia, and we have the equilibrium constant to be 3.7 times 10 to the 8th. And we want to know what happens when we have ammonia in equilibrium. Like, we don't know what the equilibrium constant is with respect to ammonia. So in doing this, we are we're reversing the reaction, which means we invert the equilibrium constant, and then we're multiplying it by 1/2 factor. That means we raise it to the 1/2 factor, same thing as the square root. And then the new equilibrium constant value is listed there as such. So questions with this one? Okay, so how are we doing for time? Yes, we have 8 more minutes. Okay. So with concentrations are pretty easy. We have equilibrium constants with concentrations, but for gases though, concentrations are kind of unwieldy for gases. We're so used to pressures, right? I mean, pressures are much easier, and especially when you're putting things into, say that you have your reaction vessel, it's much easier to deal with partial pressures of things than it is concentration. I mean, we as chemists, right? We can get concentration. Concentration is in moles per liter, but we're also used to the ideal gas law. So of course, moles per liter, it's going to be, so N over V is going to be pressure over RT, right? So we can use the ideal gas law to solve for N over V, knowing the temperature and then knowing the pressure, right? So, and knowing the volume. So we can solve for concentration, no problem. But pressure is just so much easier to deal with, right? So we have this equation here. SO3, two SO3s react to form two SO2s and oxygen. And the Kc, and usually if you see K, and if you don't even include the word C, Kc is the equilibrium concentration, or equilibrium with respect to concentration in moles per liter. But then we have Kp. Kp is the equilibrium constant in terms of pressure. So same thing with this Kc, it's products over reactants, but in this case, pressure of the product sulfur dioxide SO2 times the pressure of oxygen all over the pressure of reactant SO3 squared. And Kp and Kc are related such that Kp, the equilibrium constant in terms of pressure, is equal to equilibrium constant K in terms of concentration, Kc, times the quantity RT raised to the delta N power. The delta N is the change in the number of moles of gas. So in this chemical reaction here, we have a delta N of 1. So final minus initial. Our final is we have 3 moles of gas. Our initial is 2 moles of gas. Where am I getting 2? Where am I getting 3? There's 2 SO3s in the reactant side. So 2 species of gases. They're both gases. And there's 2 of them. And then over here, there are 2 different types of gases. 2 moles of SO2, 1 mole of oxygen. 2 plus 1 is 3. And so final minus initial, 3 final minus 2 initial equals 1. So that means if we wanted to interact between Kp and Kc, our Kp pressure, equilibrium constant in terms of pressure, for this reaction would be the Kc times the quantity RT raised to the first power. So this is an easy way if you want to invert, we can go back and forth between pressures and concentrations. So to give you an example of this, we already mentioned nitrogen monoxide. So 2 nitrogen monoxide plus oxygen, equilibrium with 2 NO2. What is the Kc for this reaction? We're given the Kp. So Kp is Kc times the quantity RT raised to delta N power. Okay. So, and what do we want? We want Kc. So that means Kc is going to be Kp over RT raised to the delta N power. And how many moles of gas we have? We have 2 moles. Oh, I already have written there. We have 2 moles on the reactant. I'm sorry, 2 moles on the product side, 3 moles on the reactant side. So delta N is equal to 2 minus 3 or minus 1. So that means our Kc is Kp RT the minus 1 equals Kp times RT. And we just plug in the numbers. So Kp is 2.2 times 10 to the, wait a second, what is this? Yeah, okay, that's right. 10 to the 12th, because that's given. Then R, 0.08206 liter atmosphere mole Kelvin. Oh shoot, I'm running out of space. Times, it's okay. Times the temperature, 298 Kelvin. That's 25 degrees Celsius, 298 Kelvin. So then if you throw that in your calculator, you end up getting 5.4 times 10 to the 13. So equals Kc. All right, so looking at this, if you have Kc and Kp and you know the balanced chemical reaction, you can use the relationship here and plugging in the number of moles. And remember, we're still at this time, the temperature has to be constant. If you change the temperature, we haven't learned this yet, but you change the equilibrium constant, kind of like the rate constant, same thing. You change the temperature, you change the rate constant. Change the temperature, you also change the equilibrium constant. So, and we have 1 minute left. Well, you have this reaction here, hydrogen plus iodine reacting to form 2 hydrogen iodides. The Kc at 620 is 620 at 25 degrees Celsius. What is the Kp? And I know there's 1 minute left. I'm going to spare you the suspense. It's actually A, because your delta N is 0. So final, you have 2 moles. Initial, you have 2. The delta N is 0. And that means Kp is Kc RT to the 0, which is Kc. So In this case, the Kp and the Kc are the same thing. So if you have no change in the number of moles, then that RT value goes away because anything raised to 0 power is 1. So, okay. There's less than a minute left to class. Anybody have any quick questions? Oh, and there's my shut up alarm. All right, so if you have questions, you can talk to me later. So I know some of you want to talk to me. If not, you're free to go.
Thank you.
Bye-bye.